This is section 9.10, part 2. All right, so last time we had developed a couple of series, and we actually proved that sine of x converged to the series that was given. If you turn to the next slide, the table there gives you a power series for elementary functions, or some of your basic functions, which we could have derived using this technique. Like 1 over x is 1 minus x minus 1 plus x minus 1 squared. You might notice that one's centered at 1. Look over at the interval of convergence. It's centered at 1, and its interval is from 0 to 2, so it means its radius of convergence is 1, because 0 is 1 away from 1, and 2 is 1 away from 1. And those intervals of convergence are important to note, because 1 over x is equal to that series on the right exactly if you pick a number that's between 0 and 2. But it would not be an exact answer beyond that interval. 1 over 1 plus x gives you that series you see, and look at its interval of convergence, etc. So I would want you to know all of the first ones. I want you to know ln of x, and I want you to know e to the x. Memorize these. Sine of x, which we've already talked about. Cosine of x, you remember that's an even function, right? Cosine is an even function. Look at what powers of x are used in that one, and what denominator values you have. They're all even numbers. Even 0. X to the 0 over 0 factorial. 0 is an even number. And so that, to me, those two, sine of x and cosine of x, are pretty easy to remember. They both are alternating. And the sine of x, being an odd function, has odd numbered powers and factorials, and cosine of x, being an even function, has even powers and factorials involved. Arctangent, arcsine, and the last one, those are ones I don't want you to worry about. So I want you to know all of them down through cosine of x. Not that those are hard, I just don't want to overtax you on this. Besides, the last ones are kind of hard. And the very last one is the one we just developed. And again, I don't want you to memorize that one. And also notice when they converge, like e to the x, sine of x, and cosine of x, all three of those converge for all real numbers. So that's kind of a comforting thought. All right, so know those. And then if you know those, then I might ask you to find a power series for a function that's related to one of those. For example, if I ask you to find f of x, a power series for f of x where f of x is the cosine of the square root of x. Well, what I'd want you to write down is the function that's related to that, and enough of its series so that I know that you have a good handle on what that series is. So I would say about 4, 5, 6 terms of it at least. Certainly no more than that. Let's do a couple more, just be on the safe side. And should I just stop after I write 8 factorial? Nope. It's not equal to that unless it's the series. If we stopped at x to the 8th over 8 factorial, it would be a polynomial that's approximately cosine of x, but not exactly. But when you put that plus dot dot dot, it makes it exactly cosine of x, which is really cool. Okay, now to do cosine of square root of x, just substitute. For every x, put in square root of x. So square root of x squared over 2 factorial plus square root of x to the 4th over 4 factorial minus square root of x to the 6th over 6 factorial plus the square root of x to the 8th over 8 factorial plus dot dot dot. And so that simplifies to be 1 minus x over 2 factorial plus x squared over 4 factorial minus x cubed over 6 factorial plus x to the 4th over 8 factorial, etc. Now, about the interval of convergence, we know that cosine of x converges for all reals. Now we have to think about what numbers we might want to put in for x if it's cosine of square root of x. And we know that we can't take the square root of a negative number and get a real answer. And so taking that into consideration, we can put in 0 because the square root of 0 is a number, 0, and it exists. But the interval of convergence is only the non-negatives. So this is the interval of convergence for the cosine of square root of x. And of course, the interval of convergence up here was all real numbers. Okay, so let's do another example. Well, before I do the one that's in your notes, I think this one will be kind of cool for you to see. If f of x is sine of x, which is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. What is the derivative of that series, term by term? Well, the derivative of x is 1 minus 3x squared over the constant 3 factorial plus 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial, and simplifying, the 3 cancels with the 3 factorial, leaving 2 factorial. The 5 cancels with the 5 factorial, leaving 4 factorial. The 7 cancels with the 7 factorial, leaving 6 factorial. And what series does that remind you of? Well, that's the series for cosine of x. Isn't that cool that that worked out? That the derivative of sine of x, which we know is cosine of x, it actually works if you do term by term. Every term of the series, take its derivative, and you get this series for the derivative function. That opens up a whole lot of possibilities. So that's really, to me, kind of cool. All right. So anyway, we're supposed to find the first 4 non-zero terms in the Maclaurin series for e to the x times tangent inverse of x. Okay, I know you probably don't have these memorized yet, so I'm going to give you what they are. E to the x is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial etc. multiplied by tangent inverse of x, which again I don't think you have these memorized yet, so I'll just give it to you. X minus x cubed over 3 plus x to the 5th over 5, etc. Now, I don't know about you, but whenever I did polynomial multiplication, when it was written horizontally like this, I found it to be kind of hard to do. So I'm going to do this multiplication in a little bit easier to understand form. So simplifying just a little bit, 1 plus x, 2 factorial is 2, so plus 1/2 x squared, plus 3 factorial is 6, so 1/6 x cubed, 4 factorial is 24, so 1/24 x to the 4th, etc. Now I've written just a few of these terms. It's possible I'm going to have to go back and write a few more, and I can if needed, because we can certainly follow the pattern, but we only need to find the first 4 non-zero terms. So I think we can do this pretty easily. So I'm going to write the other polynomial in maybe an uncommon, weird way. I'm kind of spreading things out so that they're kind of below what would be like terms. And now I'm going to multiply. And the multiplication pattern for polynomials is take the first item, let's say in the bottom polynomial, x, and multiply it by every term in the polynomial above. So I'm going to write down those results. Let me scroll down a little bit. So x times 1 is x. X times x squared is x squared. X times 1/2 x squared is 1/2 x cubed. X times 1/6 x cubed is 1/6 x to the 4th. Plus 1/24 x to the 5th, etc. And like I said, if we need to come back and do more of those to get what we're after, we can certainly do that. No big deal. Okay, then after you've done those multiplications, you now multiply the second item in the bottom polynomial, -1/3 x cubed, by each term in the top polynomial. So -1/3 x cubed times 1 is -1/3 x cubed. -1/3 x cubed times x is -1/3 x to the 4th. -1/3 x cubed is -1/18 x to the, oops, did I skip one? I sure did. Back up, let me do that correctly. Okay, so let me try again. I'm supposed to be doing -1/3 x cubed times 1/2 x squared. I think that's the one I missed. Minus 1/6 x to the 5th. I guess we could do one more, it won't hurt. Yeah, I'm not going to do more. I'm chicken. Actually, that ends up being plenty, as it turns out. Then we're going to multiply 1/5 x to the 5th times everything in above. So 1/5 x to the 5th times 1 is 1/5 x to the 5th, plus a whole bunch of stuff. Now, if you notice, since I lined things up so precisely, you may realize that the next row moves over 2 powers of x. So the first row has x, the second one starts with x cubed, the next one starts with x to the 5th. And so even though there are infinitely many things coming after this, if we now add up all of these answers, there's nothing to add to that x, there's nothing to add to that x squared, because every other line is going to just shift further to the right. So what is 1/2 x cubed minus 1/3 x cubed? Well, that's 1/6 x cubed. And what is 1/6 x to the 4th plus -1/3 x to the 4th? Well, that's -1/6 x to the 4th. And what is 1/24 x to the 5th minus 1/6 x to the 5th plus 1/5 x to the 5th? That's 3/40 x to the fifth plus a whole bunch of stuff. Now I accidentally wrote some dots implying that there might be something below the x to the fifth term, and there isn't. It's going to skip over 2 places from there. So those are the only x to the fifths that that we will encounter in this multiplication problem. We already found all 3 of them and added them together. So that means that e to the x times inverse tangent of x is approximately equal to, because we're not writing all the terms but just some of them, x, how many did they ask us to do? Plus x squared, I believe it was 4 non-zero terms, plus 1/6 x cubed minus 1/6 x to the fourth. That's 1, 2, 3, 4 terms. So I did a little bit more work than I had to, but that's okay. That is the answer that was requested. If I put the x to the fifth term, it actually wouldn't be correct according to the directions. It's correct in reality, but it's not following the directions. Okay, so let's find the first 3 non-zero terms in the Maclaurin series for cotangent of x. Now that's not in the list, but I do have 2 functions that I can divide that give me cotangent of x. That is, cosine of x is in that list, divided by sine of x. So I can do this division problem. Okay, so cosine of x is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. Hopefully I've written enough of the terms. And again, if I need more, I can always go back and throw a few more in there and expand what we're doing further if we need to. And sine of x is x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus dot, dot, dot. Now, treating these as if they were polynomials and not series. To divide polynomials, we're going to use polynomial long division, and the number in the denominator is outside. So this is x minus 1/6 x cubed, because 3 factorial is 6, plus 1/20 x to the fifth minus, oh dear, I don't have 7 factorial memorized. Let me pick up my calculator. Let's see what that is. 5040. X to the seventh plus dot, dot, dot. That's going to be divided into 1 minus 1/2 x squared plus 1/24 x to the fourth minus 1 over 720 x to the sixth, etc. Maybe one day I'll have 7 factorial memorized. I have them up through 6 factorial memorized, but not the 7. I don't know why I haven't memorized that, but nevertheless. Then in polynomial long division, you look at the first term outside, so look at x, and you think, what would I need to multiply x by to get the first term under the division symbol? So what would I multiply x by to get 1? Well, the answer to that is 1 over x. So then I multiply that answer on top by 1 over x by each of the terms in the series out in front. So 1 over x times x is 1. 1 over x times negative 1/6 x cubed is negative 1/6 x squared. Then 1 over x times 1 over 120 x to the fifth is plus 1 over 120 x to the fourth, and minus 1 over 5040 x to the sixth, plus dot dot dot. And then what we do is we subtract. So keep in mind when you're subtracting that this subtraction affects everything behind on the second line. So 1 minus 1 is 0. I never write that first thing down. Then negative 1/2 x squared minus negative 1/6 x squared is negative 1/3 x squared. And 1/24 x to the fourth minus 1 over 120 x to the fourth is 1/30 x to the fourth. And actually it ends up that's all I need, so I'm going to put plus dot 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 to save myself some trouble. Okay, so we've gone through the long division algorithm once. Let's do it again, because right now we only have one answer, 1 over x, one term of our answer. So, repeat, what do you multiply x by to get negative 1/3 x squared? Well, the answer is negative 1/3 x. So negative 1/3 x times x is negative 1/3 x squared. Negative 1/3 x times negative 1/6 x cubed is positive 1/18 x to the fourth. Yeah, x to the fourth. Plus dot dot dot. And again, if we needed to come back and add to the lengths of those, we could, and we might have actually, not knowing what was happening, gone one more just to be safe, but I'm hoping that you understand that I've done this before, and so I kind of know what we have to do. So I'm saving us a little bit of trouble. So when we subtract, negative 1/3 x squared minus itself is 0, and then 1/30 x to the fourth minus positive 1/18 x to the fourth is negative 1. Whoops, forgot to change the color of the pen. Gotta be consistent here. That's negative 1/45 x to the fourth plus dot dot dot. And the reason I could stop is that's 2 terms of my answer, and all I need is that single thing down there. Because as we've seen, to get the next number up top, we're going to think, what do I multiply the first term, x, by, to give me negative 1/45 x to the fourth? And the answer is negative 1/45 x cubed times x is negative 1/45 x to the fourth, etc., plus dot dot dot. And then when we subtract, that cancels that out, and then we would have the next highest power, x to the 6, which we won't need. So that is enough to say, therefore, that the series for cotangent of x, well, at least the first 3 non-zero terms, is going to be approximately 1 over x minus x over 3 minus x cubed over 45. Okay, so that ends this section of notes, and that's actually the end of the course as far as lectures are concerned. Very last topic. Hooray! So it's been a pleasure having you in class. I will see you in class where we can discuss anything that you'd like. Have a great day.